Asteroid mining. Asteroid mining is the hypothetical exploitation of materials from asteroids and other minor planets, including near-Earth objects. Difficulties include the high cost of spaceflight, unreliable identification of asteroids which are suitable for mining, and more extraction challenges. Thus, terrestrial mining remains the only means of raw mineral acquisition used today. The research done by asteroid sample return research missions, such as the completed Hayabusa and Hayabusa 2 and in-progress OSIRIS-RX, provides data that could possibly enable a study of future asteroid mining, although this was not the primary focus of these missions. 2. These missions are complex endeavors and return a small amount of material for the size and expense of the project, though these small samples are enough for researchers to study and analyze. 2. There are major technical hurdles in the way of potential asteroid mining. 4. Asteroid mining shifted to a more distant long-term goal, and some asteroid mining companies have pivoted to more general-purpose propulsion technology. Minerals in space. As resource depletion on Earth becomes more real, the idea of extracting valuable elements from asteroids and returning these to Earth for profit, or using space-based resources to build solar power satellites and space habitats becomes more attractive. Hypothetically, water processed from ice could refuel orbiting propellant depots. Although asteroids and Earth accreted from the same starting materials, Earth's relatively stronger gravity pulled all heavy hydrophilic elements into its core during its molten youth more than 4 billion years ago. This left the crust depleted of such valuable elements until a rain of asteroid impacts reinfused the depleted crust with metals like gold, cobalt, iron, manganese, molybdenum, nickel, osmium, palladium, platinum, rhenium, rhodium, ruthenium and tungsten. Today, these metals are mined from Earth's crust, and they are essential for economic and technological progress. Hence, the geologic history of Earth may very well set the stage for a future of asteroid mining. In 2006, the Keck Observatory announced that the binary Jupiter Trojan 617 Patroclus, and possibly large numbers of other Jupiter Trojans, are likely extinct comets and consist largely of water ice. Similarly, Jupiter family comets, and possibly near-Earth asteroids that are extinct comets, might also provide water. The process of in situ resource utilization, using materials native to space for propellant, thermal management, tankage, radiation shielding, and other high-mass components of space infrastructure, could lead to radical reductions in its cost. Although whether these cost reductions could be achieved, and if achieved would offset the enormous infrastructure investment required, is unknown. Ice would satisfy one of two necessary conditions to enable human expansion into the solar system: physical sustainability and economic sustainability. From the astrobiological perspective, asteroid prospecting could provide scientific data for the search for extraterrestrial intelligence. Some astrophysicists have suggested that if advanced extraterrestrial civilizations employed asteroid mining long ago, the hallmarks of these activities might be detectable. Asteroid selection. An important factor to consider in target selection is orbital economics, in particular the change in velocity and travel time to and from the target. More of the extracted native material must be expended as propellant in higher V trajectories, thus less returned as payload. Direct Hohmann trajectories are faster than Hohmann trajectories assisted by planetary and or lunar flybys, which in turn are faster than those of the interplanetary transport network, but the reduction in transfer time comes at the cost of increased V requirements. Citation need. The easily recoverable object subclass of near-Earth asteroids are considered likely candidates for early mining activity. Their low V makes them suitable for use in extracting construction materials for near-Earth space-based facilities, greatly reducing the economic cost of transporting supplies into Earth orbit. The table above shows a comparison of V requirements for various missions. In terms of propulsion energy requirements, a mission to a near-Earth asteroid compares favorably to alternative mining missions. An example of a potential target for an early asteroid mining expedition is 4660 Nereus, expected to be mainly enstatite. This body has a very low V compared to lifting materials from the surface of the Moon. However, it would require a much longer round trip to return the material. Multiple types of asteroids have been identified, but the three main types would include the C-type, S-type, and M-type asteroids. 1. C-type asteroids have a high abundance of water which is not currently of use for mining but could be used in an exploration effort beyond the asteroid. Mission costs could be reduced by using the available water from the asteroid. C-type asteroids also have a lot of organic carbon, phosphorus, and other key ingredients for fertilizer which could be used to grow food. 2. S-type asteroids carry little water but are more attractive because they contain numerous metals, including nickel, cobalt, and more valuable metals, such as gold, platinum, and rhodium. A small 10-meter S-type asteroid contains about 650,000 kilograms of metal with 50 kilograms in the form of rare metals like platinum and gold. 3. M-type asteroids are rare but contain up to 10 times more metal than S-types. A class of easily recoverable objects was identified by a group of researchers in 2013. 12 asteroids made up the initially identified group, all of which could be potentially mined with present-day rocket technology. Of 9,000 asteroids searched in the NEO database, these 12 could all be brought into an Earth-accessible orbit by changing their velocity by less than 500 meters per second. A dozen asteroids range in size from 2 to 20 meters. Asteroid cataloging. The B612 Foundation is a private non-profit foundation with headquarters in the United States, dedicated to protecting Earth from asteroid strikes. As a non-governmental organization, it has conducted 2 lines of related research to help detect asteroids that could one day strike Earth, and find the technological means to divert their path to avoid such collisions. The Foundation's 2013 goal was to design and build a privately financed asteroid-finding space telescope, Sentinel, hoping in 2013 to launch it in 2017 to 2018. The Sentinel's infrared telescope, once parked in an orbit similar to that of Venus, is designed to help identify threatening asteroids by cataloging 90% of those with diameters larger than 140 meters, as well as surveying smaller solar system objects. Data gathered by Sentinel was intended to be provided through an existing scientific data-sharing network that includes NASA and academic institutions such as the Minor Planets Center in Cambridge, Massachusetts. Given the satellite's telescopic accuracy, Sentinel's data may prove valuable for other possible future missions, such as asteroid mining. You can find the source I use in the description. Don't forget to subscribe and stay healthy.